Hello, this is the first of the videos on university level physics where we'll be starting off with the undergraduate course, and the topic that we are going to start with is electricity and magnetism. Now, in this case, to start this thing, we'll be going back to the high school level where we have electrostatics. The electricity part starts with electrostatics that deals with the static charges. Now we all have studied. I'll be just giving you a briefing you through the electrostatic part, and we'll be doing a few, at least one of the numericals in this first video uh, within our stipulated time. Now, if we have charges, and obviously the charges without the influence of any field or voltage will remain static, but nevertheless they will apply some force on one another. To get a detail about the initial part of it, you can refer to the electrostatic videos that I have made previously. So if we are considering two charges which are separated by a certain distance, let us say r, the charges being q1 and q2, as per Coulomb's law, the force between them is obviously some constant times the product of the two charges divided by r squared, that is inversely proportional to the square of the distance between them, and that constant being 4 pi epsilon naught, 1 by 4 pi epsilon naught being the permittivity of free space that has all been dealt with previously. So this is the expression for the magnitude of the force. Now obviously the force is a vector quantity. The first charge over here will, if it applies a force along this direction, probably repulsive, the same nature of charges, and this charge similarly provides or pushes this charge along this direction, and let us say if it is force on 2 due to 1 and this is force on 1 due to 2, as you know, this is simply the action and reaction case where we have the forces to be of equal magnitude but oppositely directed on different bodies, of course. That is, q1 is applying a force on q2, and q2 on the other hand is giving a reaction force to q1. So there are two separate forces on separate bodies, but nevertheless they constitute together the action and reaction forces. Now, as far as the distribution of charges is concerned, we probably have a discrete system over here which is applying a certain force on any charge q which is placed over here. Remember, this has all been dealt with previously, but just for the sake of continuity into this topic, we'll be starting off with these things. So let the position of this charge q, capital Q, with respect to the small q be r1, the position vector considered vectorially, and similarly we have r2, r3 and r4 for all the rest of the charges that are placed over there, r4, and there may be multiple number of charges, discrete charges over that region, and similarly you will have different uh, position vectors. Now we want to determine the net force that is acting on that charge q. Now remember, these charges q1, q2, q3, they will be applying forces on one another as well, but the question here is for the charge q which is placed separately from that distribution. So the force on that charge will be considered individually, uh, the individual forces that will be acting due to the discrete charges, that is for Q1, for Q2, for Q3, and all the other charges that are present over there, whole range of them on that charge Q. So we have F1 supposedly is the force on Q due to Q1. So we have KQQ1 divided by R1 squared along R1 vector, so R1 cap. Similarly, we will be having forces F2, F3 and F4 as well. Let's not get into the detail of it, but we'll be, because the forces are vector quantities, or forces are vector quantities, so the net force obviously is the sum of all these individual forces. But what kind of sum? Obviously it is the vector sum of all these individual forces that are acting on it. That is what is known as the principle of superposition, which has been dealt with in case of waves and other stuff. uh, this involves a vector, not the algebraic sum. But in potentials, obviously, we are considering scalar quantities, and therefore the sum in that case will be algebraic, but that is to be uh, dealt separately in some other videos. We have, in fact, as I say time and again, we have discussed it previously in our videos on electrostatics. Now, with this information available, we can extend this to a continuous system. Now, in case of a continuous system, we have the distribution not in the discrete form, I should say, but in the form just as in case of uh, you know some kind of liquid or paint smeared on a surface. That forms a continuous system where you cannot really count the numbers over present over there. So had there been some spots, then we can identify them. But these are not spots, these are some simply smearing of the charge. Now you can take the example of this, a handful of sand. Now in case of sand, you have sand grains, you can actually count them, but they're never counted because there are plenty in numbers, so they can be treated as a continuous system, but nevertheless they can be counted. But who counts them? Because they are in plenty. So is the case with charges. The charges that are present within a given surface or within a given object can be plenty in number, uh, nearly 10 to the power 20 and above. So it's not really possible to count each and every one of them. In fact, you cannot count them. So that is why the system mostly are in the form of continuous system and not the discrete ones. However, the discrete ones help us to understand the continuous system, the the essence of the continuous system as a whole. Now, before moving over to the continuous system, we can, however, uh, discuss a bit about the field. Now, the electric field, now the charges that apply force on one another, they apply the force along a certain line, and they are known as the lines of force. And the field is exactly the influence of these lines of force, the ambit or the territory within which these lines of force make any form of impact. And therefore the electric field, usually represented as E vector, is simply the force that is acting on a particular charge per unit test charge. Now suppose I want to determine the field intensity of this charge Q over a distance r. Now how do I do that? Well, I just place if there is nothing to say, if there is nothing there to predict the force or the impact, then I won't be able to say. So what I do is I place a test charge over there just for the sake of testing the amount of force that can possibly act on at that point due to this charge that is given over there. So the force obviously is Q naught divided by R squared as per Coulomb's law. We are just concerned about the magnitude in this case. And but There was no charge initially over there, was there? Was it? I just placed it for the sake of determining the force at that point, the impact of the force rather. So once I know the impact, I can just get rid of that test charge. And how do I get rid of it? I get rid of it mathematically. I just set the limit q0 tending to 0. Now with that limit available, what I can do is I set q0 tends to 0 and 1 by q0 is present over here. For the force, I just keep kq q0 divided by r squared. If in case of vector we have r cap, that is the direction along which the force acts, and the q naughts can cancel out each other, what we are left, and now we can apply the limit with the q naughts vanishing. uh, Setting the limit q0 to 0 doesn't make much of a difference. We are left with kq divided by r square r cap. So this is probably, or this is essentially the expression for the electric field intensity at any given point due to a given charge. This is the given charge capital Q. Due to that, at a distance r, we have the electric field intensity, or so as to say the impact of itself in that region is what this calculates. Now, as this is vector quantity, we can have a discrete system of charges just like in the above figure or above case, and we can calculate the impact, the net impact of all those charges at a particular point, and the story goes in the same way that the net electric field is obviously the vector sum of all the individual electric fields that is available due to the individual charges placed at that point. Again, this is a result of the principle of superposition and is quite similar to the above discussion. Now, if we are to just get into the continuous part of it, let's see what we have in store for us in the continuous system. Let me add another page for that. Now, in case of the continuous system, what we have is that suppose we can have a linear charge distribution where the charge, an amount of charge, probably Q, is distributed uniformly over this entire length L, and as a result of that, we have Q amount of charge to be distributed over that entire length. So, or let me write it the other way around, that L length has Q amount of charge, so a unit length will have Q by L amount of charge. Remember that three bars that I draw over there, they represent the equivalent sign, because we can only use equal to signs uh, in case of the same dimensions on either side. So that is why I have used that equivalent sign instead of that equal to sign. So L has an equivalent Q amount of charge, so a unit length will carry Q by L amount of charge, and that is defined as lambda, that is the linear charge density. Now what about the case of a charge distribution, a linear charge distribution, just like this, just like in the case of a wire, wobbly wire, probably not a straight one. And here we have a point where we want to determine the electric field intensity due to that entire uh, linear charge distribution. Now remember, this has a charge Q distributed over its entire length, uh, where the charge per unit length is obviously lambda, that is the um, linear charge distribution. And obviously you have different points to be at different distances, and it's not that it's a discrete system, so you have single points singled out and you can calculate them easily, but this is a continuous system, so the easiest way to move along with this continuous system is to just integrate it. Now instead of taking a point, I can consider an infinitesimally small segment of it, probably dx, or dl, dl being an elementary length, which is probably at a distance, let us say r, which keeps on varying in this case. R is the position vector of the point with respect to the dl element. Now the charge that is carried by that dl element is obviously charge per unit length multiplied with that length, that is lambda times of dl. This is a small amount of charge dq which is carried over by that elementary length dl. So the electric field, as per the expression, we first of all take the modulus of it, that is k dq divided by square of the distance. So in this case what we have is that k dq, instead of dq we can use lambda times of dl divided by r squared, and that is the magnitude of it. But considering the entire electric field as a whole, we have to consider the vector case where we have the directions involved. And the direction here is along the r cap vector. So k times of lambda times of dl divided by r square r cap. This is the, now this is obviously this small electric field due to this small element dl. The net electric field will be an integration of this over that entire length. We will choose suitable limits as per the given parameters. Now let's take an example which will help you to understand this in a better way. Suppose we want to calculate the electric field intensity at a point which is lying at a distance z along the z-axis. This is probably the z-axis, right? And it is lying at a distance of z from a charge distribution which is of length 2l. 2l, that is, we take a midpoint O, and from that we can take this as the negative length minus L, and this as the positive length L. Now the charge distribution is lambda, is uniform with linear charge density lambda. What we want to find is that we want to find the net electric field at the point P due to this continuous charge distribution. Now in order to do that, we can consider this to be as the x-axis, the axis along which the linear charge distribution is available, and from that we consider two symmetrical elements at a distance x. Now let this be an element dx which is lying at a distance x from the central point, and similarly we take another symmetrically placed element dx. Now why do we take two elements? Why was there even a necessity of choosing a center at O? All that can be answered when we proceed to the solution part of it. Now from this element, let the disk, now this is at a distance z. From this element we have the distance towards the point P as let us say it is r as of now. So r is the position vector of P with respect to the element dx. And similarly here also we'll have the same magnitude as r because the dimensions are pretty same in this case, but the direction obviously changes, so probably we can take it as r dash. But remember, r dash and r have the same magnitude, just denoted differently because of the directions involved. Now from this point P you have the electric field for a positive test charge placed over there. The electric field, and this charge distribution is obviously a positive charge distribution. If it's not mentioned to be negative, then we can take it as a positive charge distribution. Now This electric field obviously will be directed away, because if I place a positive test charge at the point P, it will be repelled by this positive charge distribution, or by the positive charge that is present in that segment of dx, infinitesimally small segment dx. Similarly, we'll have the electric field to be along that direction due to this element dx, although it's not in a straight line, but we can assume that. Right, now let this angle over here be theta. So is this angle, because of the symmetry involved, and so are these angles because of the vertically opposite angles that are present. Now this is supposedly DE, and this is DE dash. Again, the notation DE dash, DE, although they are same in magnitude, but they will be differently denoted because of the directions involved. Now DE dash, as I mentioned, I must mention it over here, DE dash is simply of the same magnitude as the E, and as you can see, they both of them will be having two components. Now DE dash and DE will have their cosine components to be acting along that z-axis that we have taken, that is DE cos theta and DE dash cos theta will be acting along that line. And what about the sine components? Now the sine components will be acting in opposite directions. Now with the magnitude being equal and the directions being opposite, these two components will simply cancel out each other. And that is why it was ideal for us to take two elements on either side, because with two elements available on either side, the sine components, or the vertical components, so as to say, here they are obviously horizontally placed, they cancel out each other. So for each dx that I take along this while integrating, because we will definitely be integrating along that line, so each dx element that I take along the x-axis, they with symmetry available, the sine components will get cancelled while the cosine components will be lying along that line, which also tells us that the resultant electric field will be acting along that line as well, because that is the component that's available. Rest that is the horizontal components, in this case the sine components, are cancelling out each other. So finally we have the net electric field dE to be a sum of dE cos theta plus dE dash cos theta. Now because they are acting along the same line, we can just choose the magnitude and just add them directly, because you know that dE dash and dE are the same thing. So we have this to be as 2 dE cos theta. Now what is the value of dE in the first place? The dE is equal to k dq. What is dq? Dq is equal to lambda times of dx, as in this case, as in the previous case we had taken dl, here we have taken dx, so it is lambda times of dx. K dq divided by the square of the distance, that is r square. Remember, we are considering the magnitude only. So this is the value of dE. Now it's not as easy as it looks, because the integration involves certain critical things over there. Now 2k, that is the value of dE, I'm putting it over there, 2k lambda cos theta dx divided by r squared. Now in case of r squared, the value of r is changing every time I shift the dx along that line, because we have to consider that entire line from 0 to this point L and this point minus L on the other side. So what we do is we get rid of those variables over there, and if we place the variable has to have a certain limit over which we can integrate. So the net electric field, in order to determine that, what we do is we have this triangle available to us. In fact, we have two symmetrical triangles, and in those triangles, if we consider the case of tan theta, what about tan theta in each case? Tan theta will be simply equal to uh, the perpendicular divided by the hypotenuse. Now the perpendicular is x in this case, which is in front of the angle. Here it is the right angle triangle over here. So perpendicular is x divided by the hypotenuse in each case is r. Remember, r and r dash have the same magnitude. They can be taken as r for our convenience. Now, so we have x to be equal to r tan theta. Because x is equal to r tan theta, here it is simply dx can be taken as dx is equal to r sec square theta d theta, because dx by d theta on the left hand side will give me d by d theta of r tan theta. R can stay out. D by d theta of tan theta is sec square theta, and the d theta got cross multiplied. So we have dx is equal to r sec square theta d theta. Now with that gone, what we have is we can substitute dx for that, and again, because we could have taken the limit over dx from 0 to L, because x is varying from 0 to L. Now we will have to change limits in case of theta. What do we do then? Well, we just proceed as per the rules. What are the rules over there? Before that, once again, we can do one more substitution over there, because we have r square over there. Instead of r, what we can do is we can just take r as instead of r we will require theta over there. So how do we substitute that? Well, I made a small error over here, that is x divided by z is tan theta. My bad. So it is x divided by z, which is tan theta. So x is equal to z tan theta, and dx is equal to z sec square theta d theta. Now in that r square over there, what we have is r square is simply equal to z square plus x square in this case, because with the x varying, you have the value of r varying as well. And from the look of it, what we have over here is that x y z is equal to tan theta. So x obviously is equal to z tan theta. Z square plus z tan theta whole square. That gives me z square plus z square tan square theta. That gives me z square taken common. 1 plus tan square theta is simply sec square theta. So z square sec square theta. That lies in the denominator instead of r square. Now we have a fixed value, and we have just the angles to deal with. Let's take the other page. Now with all the parameters available, I'll be writing down this equation from the previous page so that it gets easier for us to. I'll be rewriting the equation from the previous page. What we had in the previous page is that dE net, go back to the previous page, dE net is equal to 2k lambda cos theta. 2k lambda cos theta. What do we have instead of dx over there? Dx is simply z sec square theta d theta. Z sec square theta d theta divided by the value for r square is z square sec square theta in the denominator. Z square sec square theta in the denominator. The sec square thetas can get cancelled out, and one of the z's can cancel out as well. So what we have is the magnitude, of course, 2k lambda divided by z. All these fellows are constant, cos theta d theta. Now the integration will obviously be over the angle now. So the net electric field is simply the integration of the dE net, and that is equal to 2k lambda divided by z cos theta d theta integrated. But the question is, what should be the limit in case of theta? When it was x in the previous case, let me go back to the previous page. When the limit over there was x is equal, now let's take the case where x is equal to 0. For x is equal to 0, you have tan theta to be equal to 0 as well, and for that theta must be 0. So the lower limit in this case, for instead of x is equal to 0, you have the theta to be equal to 0 as well. Let me just write that down for you on this page for a better understanding. We had the limit initially we had 2k lambda cos theta dx by r square, 2k lambda cos theta dx divided by r square. That was integrated over dx, and when we are integrating over dx, you had this triangle where it was varying from 0 over here, 0 to this value over here, that is L, right? So from 0 to L was the variation of x on either side, because we had the factor 2 over there, or in case of integration, now it comes because of the addition of the cosine components, two cosine components. So what we do is that we had the integration from 0 to L. Now, because the limit must be changed with the integration on which this is being done, what we have over here is that since x by z is equal to theta, for x is equal to 0, you have theta to be equal to 0 as well. So that's the lower limit. Now for x is equal to L, what do we have there? When x goes to L, over here, right, the value of theta is somewhat like this. I'll redraw it in the next page. The value of theta, if you observe this is z, this is entirely L, this was r, which keeps on varying. We need not care about the variables, we only want fixed values. Here is the theta. Now theta can be taken as if we have sine theta over here. What is the value of sine theta? Sine theta is simply L divided by r. That means L divided by, what is the value of r? Value of r is, in this case, using Pythagoras theorem, is z squared plus L squared under root. So that's the value of r. So theta is simply sine inverse of L divided by z square plus L square taken under root. Why I have considered sine inverse and not cosine or anything like that? Well, that's because the cosine integration will give me a sine value over there. So sine of sine inverse will get cancelled out. Let's check it if our assumption is correct. So 2k lambda divided by z. Now the upper limit of theta for x is equal to L is simply sine inverse of, although that may seem pretty non-trivial, but it's my method, so I'll support it in some way. So this is the integration is obviously sine theta. Sine theta taken theta from limit 0 is sine inverse of this particular thing, that is L divided by Z square plus L square under V. Now, so this gives me 2k lambda divided by Z sine of the first value, that is sine of sine inverse of L divided by Z square, that is the upper limit over here, minus sine of theta is 0 in the lower limit. Sine 0 goes to 0, as you know. I'm doing this over here. So 2k lambda divided by Z. Sine of sine inverse cancelled out. So all that you're left is L divided by Z square plus L square. This is the value of the next electric field, and we know that this electric field vectorially acts along in the Z direction because we have a positive charge. This is gone slowly. You can shift part as you know of, and you can obviously do integration in a much efficient way, but I believe I it's easy to understand, although it may seem precarious or maybe difficult. This seems to be pretty easier to me, so I followed this, followed it up with it. So now we can have certain cases, certain other cases associated with it. What if this Z that we see over there is double greater than L? That means this point that we have over here, it extends to a much greater distance, such that L is very small for us, and L being small, so is the case with 2L, right? So that entire linear segment, linear charge distribution segment, is pretty small in comparison to a very large value of Z. In that case, this above equation can be rewritten. We can go for the magnitude once again. We have 2k lambda. We have the Z over here. This Z in the denominator can be taken out of the bracket, out of that square root. And with that taken outside, we have another Z outside over here. What remains within that is 1, and this is L squared divided by Z squared, and the L obviously remains above. We have the magnitude, so we don't care about this term. So here the L square by Z square term can nearly go to 0, because that becomes very small when compared to the addition with 1. So what we have finally is 2k lambda L divided by Z square. Now 2L is the length of that entire thing, and that length multiplied with that charge per unit length is simply the charge itself, that is K, and lambda times 2L is Q, because the charge distribution is over the entire length 2L divided by Z square. So what does this mean? This is exactly the expression for a point charge which is lying at a distance of suppose Z from another point where the electric field intensity is determined. It means this length, this entire length that we have over there, has been reduced to one only, and that's quite fair when you compare larger distances. The length obviously will